Good morning, gentlemen. Today is Tuesday, March the 24th, and we are again here in the bunker at the RAP compound, and I am going to give you a lesson on the law of conservation of energy. If you recall from last week, we talked about the idea of energy in terms of kinetic and potential. And we also have talked many times about laws of conservation. Just a few weeks ago, we talked about the law of conservation of momentum. And I'm certain that you've heard of the law of conservation of energy before this, possibly with Mr. Leonard last year in chemistry, and certainly in a physical science class in 8th grade, whether it was with Mr. Coleman here at LaSalle or with someone else. In any event, the law of conservation of energy simply states that energy can neither be created nor can it be destroyed. Now, that means that the total amount of energy in the universe, or in any given system, whatever that system happens to be, is a constant. It doesn't change as time goes on. And so that's the premise we're going to start with today. All right, energy can neither be created nor destroyed. Now, that's not to say that we can't transform energy from one type to another. We can certainly take fossil fuels and convert it into mechanical energy to drive our cars down the road. We can take fossil fuel energy and convert it into steam or heat, which can be converted into electricity, or which can be then turned into light or whatever it is to run the computer, for example, that you're working on now. But in any event, the law of conservation of energy says that energy can neither be created nor destroyed. Now, in terms of physics, the most interesting aspects of this deal with kinetic and potential energy. So, for example, if you were to take an object and throw it out or off of a cliff, all right, or something like this, for example, in example number 7, a 10-kilogram object falls freely from rest from a height of 20 meters above the Earth. I want you to calculate its gravitational, its kinetic first, gravitational potential, and then total mechanical energies at 5-meter intervals until it reaches the ground. Okay? Now, you can imagine this as an object, falling out of an airplane or falling out of Santa's sleigh on Christmas Eve, or if you're just ticked off at someone, you can throw him out or off of a cliff and watch him fall to the ground. Now, how do we actually approach a problem like this? Well, we know that the formula for kinetic energy is Ke equals 1/2 mv squared, where m, of course, is the mass of the object, and v represents the final velocity. The potential energy is, of course, mass times the acceleration of gravity, which is mass, mg is weight, times the height above the ground. Now, the interesting aspect of this is that the velocity that you deal with in a kinetic energy equation is really the final velocity of the object, wherever it is in its motion downward. And so Vf squared, or that v squared in the kinetic energy formula, is equal to Vo squared plus 2 times the acceleration times delta y. This is one of the kinematics formulas that we learned very early on in September. But because the initial velocity, at least in example 7, is 0, the Vo squared term cancels out, and I'm left with the final velocity squared equals 2g times delta y, how far we've fallen, delta y. And so I can rewrite the kinetic energy formula as 1/2 times 2, 1/2 times m times 2 times gy. But since 1/2 times 2 is equal to 1, I can even simplify this further and get Ke equals m times g times delta y. Notice the similarities between the kinetic energy formula in this form and the potential energy formula that we've got in the upper right-hand corner there. All right, the difference between those two formulas is that delta y is how far down we've come from the top, whereas h is how far we are from the ground, from the bottom. Now, let's get back to example number 7 so that we can actually look at how to solve a problem like this. So a 10 kilogram object falls freely from rest from a height of 20 meters above the Earth. Calculate its kinetic, gravitational potential, and total mechanical energies at 5-meter intervals until it reaches the ground. So how do we approach this? All right, well, the first thing that we're going to do is, of course, make ourselves a laundry list. Now, this is going to be a quick and modified laundry list in terms of what we've got here. We know that the kinetic energy is going to equal 1/2 mv squared. We know that the potential energy is going to be mass times the acceleration of gravity times height. Now, in this case, we're going to know that of course, we're obviously going to adapt our kinetic energy formula to be m times g times delta y. Now, that leads us to our laundry list here. So we know that the object has a mass of 10.0 kilograms, and so that will be our next little addition. So m equals 10.0 kilograms. Okay. It's 9 o'clock. Well, thank you, Jesus. The acceleration of gravity is, of course, or I'm sorry, the initial velocity, that should be right here, this should be a subscript O, is 0 meters per second. The acceleration, of course, is the acceleration of gravity, which is 9.81 meters per second squared. And of course, we start out with a height above the ground at 20.0 meters. Okay, so there's our basic laundry list. We'll have to adapt this for each particular problem. But in order to solve this, what I want you to do is to build yourself a table. Okay, the table itself will have 4 columns. The first will be height above the ground, and we were supposed to do this in 5-meter intervals. So we're going to have 20, 15, 10, 5, and 0 meters above the ground. The second column will be kinetic energy using the formula mg delta y. The third column will be potential energy using the formula m times g times h. And the fourth column will be total energy, which is simply the sum of the kinetic and the potential. And this is what that leaves us here. All right. Notice the height above the ground is given in 5-meter intervals, 20 to 15, all the way down to 0. Now, in the kinetic energy formula, I haven't rewritten, or in the kinetic energy column, I haven't rewritten the formula, but 10 kilograms is equal to the mass. 9.81 meters per second squared is the acceleration of gravity, and 0 meters is the delta y value when I'm still 20 meters above the ground. And so the total kinetic energy when I first let this thing go is 0 joules. Same thing in the second row of that column. Mass is 10, acceleration of gravity is 9.81, but now we've fallen a total distance of 5 meters. When we go from 20 to 15, we've fallen 5 meters. And so 10 times 9.8 times 5 is 491 joules. Now that's a rounded number. It comes out to be like 490.0, I think. But we have to use correct sig fig, so it's 491. At 10 meters, we have a total kinetic energy, 10 times 9.81 times 10, which is 981, and so on and so on. Notice that the kinetic energy at the bottom is 1,960 joules. Now in the potential energy column, we do the same thing. Mass times the acceleration of gravity times the height is 10 times 9.81 times 20, or 1,960 joules. Again, a rounded number. At 15 meters above the ground, we've got 10 times 9.81 times 15, or 1,470 joules, and so on, all the way down. And notice, at the instant we hit the ground, the gravitational potential energy is 0 joules. Okay? 0 joules. Now, here's the cool thing about this, all right? Notice, If you add up the two rows for kinetic and potential energy at each height above the ground, you get the same total energy in that last column. 0 plus 1,960 is 1,960. 491 plus 1,470 is 1,960. 981 plus 981 is 1,960, all the way down. So again, this demonstrates the law of conservation of energy. Right? The total energy in the system is the same, right, all the way down the column. Now, another aspect of this law of conservation of energy is in dealing with a pendulum. Okay, now pendulums are examples of gravitational and kinetic energy. Okay, I got to move this thing so that it's actually in my picture here. But the picture on the screen will show you and slowly will build a pendulum as it swings back and forth. So here I've got my handy dandy trusty hand sanitizer. Ooh, got to make sure you have that in the house. All right, there's no freaking toilet paper around, but you can get hand sanitizer at my house. All right. In any event, when a pendulum swings from its highest height down to its lowest height, two things are happening. All right. The first is that its kinetic energy is going from 0 at the top of its swing to its maximum at the bottom of its swing, and then back up to 0 at the top of the swing on the other side. Okay. The potential energy, of course, gravitationally, is highest when it's at its highest point here, okay, and minimum at its lowest point here. And so in the diagram that I've got drawn on the screens here, I've got 3 different locations of the pendulum illustrated. Location A, B, and C. And at each of these positions, we've got different amounts of kinetic and potential energy. Now, very quickly, if we go through this, at positions A and C, we are at the maximum amount of gravitational potential energy. Notice I haven't given you a number here because that depends on the height above the ground and really the height above the point B. But there's no kinetic energy because at points A and C, it has stopped its motion to turn around and swing back. At point B, you've got maximum kinetic energy and minimum potential energy. But just like in the object that's falling out of Santa's sleigh, the total energy is the kinetic plus the potential at any given point. Okay, so your homework for this evening is to do the question number 9 on the homework sheet. This is a question regarding an object falling from a height down to the ground, and I'm going to ask you to calculate the kinetic and potential energies as well as the total energies all the way down here. Gentlemen, happy Tuesday. I hope that you are all safe and well. All right, we are on day 5 of Lessons from the Bunker. I hope that you're actually getting something out of this. All right, good luck, God bless, and may the force be with you.